These are your notes for Unit 2, Day 3 of Calculus. If you would like to see the warm-up, the review question, or any homework questions we covered in class today, just look at the finish notes. So today we're going to talk about the derivatives of sine and cosine and the other trig functions. We're going to first find the derivatives of sine and cosine by using their graphs and graphing their derivatives. Then we're going to talk about two new derivative rules, the product rule and quotient rule, and then we'll use those rules to find the derivatives of the other four trig functions. So finding the derivative of sine x by graphing. So if you remember from a previous class, the first thing we want to do when we're finding the derivative of a graph is we want to find where the derivative, or the slope of the tangent line, would be 0. Well, on a sine graph, the slope of the tangent line is 0 at the peaks and valleys. So the derivative would equal 0 at negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. And then after that, we have to decide where is the original function, the sine function, increasing, because where it's increasing, like here, from negative pi over 2 to 3 pi over 2, the derivative is positive. And when the derivative is positive, its y values are above the y-axis, or above the x-axis. So from negative pi over 2 to 3 pi over 2, the derivative is positive, so it's going to exist above. And then from negative 3 pi over 2 to negative pi over 2, notice the original function is decreasing. That means the slopes of all of its tangent lines are negative. So the derivative would be negative, so it would exist below the x-axis, so it'll be down here. And then from negative pi over 2 to pi over 2, all of the slopes of the tangent line, all of the derivatives would be positive. So they'd exist above the x-axis. And again, they have to go through all of those pink points because that's where the derivative would have been 0. And then from pi over 2 to 3 pi over 2, the original function is decreasing, so the derivative would be negative. So it exists below the x-axis. And then after that, it's positive, so it'll exist above. Now notice that green line. What did we just graph? So if you look at this green line, what is the green line the graph of? It looks very similar to sine, but it starts at 1 instead of starting at 0. That's the graph of cosine. So the derivative of sine. So if y equals sine x, then the derivative, dy over dx, is cosine x. The derivative of sine is cosine. If we wanted to find the derivative of cosine by graphing, we'll go through the exact same process. So the slope of the tangent line would be 0 at negative 2 pi, negative pi, at 0, at pi, and at 2 pi. And then the original function is decreasing between negative 2 pi and negative pi. So the slopes of the tangent lines would be negative, so the derivative would be negative. So it exists below the x-axis. And then between negative pi and 0, the slopes of the tangent line are positive, so the derivative would be positive. And then the slopes of the tangent line are negative between 0 and pi, so the derivative would be negative. And then between pi and 2 pi, the slopes of the tangent line are positive, so the derivatives would be positive. Now notice, what did we just graph? So that graph looks like a graph we know. It crosses through at 0, but it goes down first. So it is the opposite of sine. So the derivative of cosine is negative sine. It's the reflected sine graph. So the derivative of cosine is negative sine. And so those are two derivatives you should memorize. The derivative of sine is cosine, and the derivative of cosine is negative sine. So now let's talk about some important rules. So we remember the power rule from last class, or where you just multiply by the exponent and subtract 1 from the exponent. Now we're going to talk about the product rule. So if you have two different functions that are being multiplied, so notice in my f of x at the top, we have x squared plus 1 times x squared minus 2x. So the product rule says if you are multiplying two functions, so if you have f times g, then the derivative of that would be you take the derivative of the first function, f, and you multiply it by the second function, just the original second function, and then you leave the first function alone, and then you multiply by the derivative of the second function. So the derivative of f times g is you take the derivative of the second function, leave the first function alone, take the derivative of the first function, leave the second function alone. And it doesn't really matter what order you're doing it in because you're adding. So the commutative property says you can take the derivative of the first function times the second function plus leave the first function alone times the derivative of the second function. So the product rule says if you want to take the derivative of two functions that are being multiplied, take the derivative of the first function, then multiply that by the second function, the original second function. Then it's plus in the middle. You write the first function and times it by the derivative of the second function. So for this one, the derivative of f prime of x would be the first function is x squared plus 1. So the derivative of x squared plus 1 is 2x. So I'm going to take the derivative of 2x, then I multiply that by the second function, x squared minus 2x. And then I'm going to add that to, now I'm going to take the derivative of the second function, and the derivative of the second function is 2x. And then I multiply that by the first function, x squared plus 1. And again, the order in which you multiply the first two pieces or the order in which you multiply the second two pieces doesn't matter. And you can add them in either order. So I could do the pink before the green or the green before the pink. All right, so second time, we have x to the third times cosine x. So x to the third could be my first function, and then cosine x could be my second function. So if I want to take the derivative of this, it's a product. It's one function times another. You take the derivative of the first function, and then you multiply it by the second function. So it'll be 3x squared times cosine x, and then it's plus in the middle. And then you can take the derivative of the second function. The derivative of cosine is negative sine x, and then multiply it by the first function, x to the third. And you could also write it as 3x squared cosine x, and then since it's a positive and a negative, it'll be negative. And we typically write the polynomial function before trig functions. You don't have to, but we would write this as negative x to the third and then sine x. Either way is okay. So let's go ahead and do some more. So differentiate each function. So we have the first function, the cube root of t, which is t to the 1/3 power. And then we are multiplying that by t to the second plus 4. So if I wanted to take the derivative of h, take the derivative of the first function, so 1/3 t to the negative 2/3, and then leave the second function alone, t squared plus 4, and then plus take the derivative of the second function. The derivative of t squared plus 4 is 2t, and then times, leave the first function alone, t to the 1/3, or you could write that as the cube root of t. And you can leave it like that. On the next one, we have x to the second times sine x. So if I wanted to take the derivative of this, the derivative of the first function is 2x, then times, leave the second function alone, sine x, and then plus, and then the derivative of sine x is cosine x, and then times x squared. And again, typically we write the polynomial function first when you're multiplying, so it would be 2x sine x plus x squared cosine x. But either way is okay. So that is the product rule. The quotient rule is when you are dividing two functions. So notice in f of x we have x divided by x squared plus 1. So it's one function divided by another function. So the quotient rule says if you have f over g and you wanted to take the derivative of that, you take the derivative of the top and then you multiply it by the denominator function. So you take f prime times g, and then for the quotient rule we subtract in the middle, and then you can leave the top function alone, and then you can multiply it by the derivative of the bottom function, so f times g prime, and then all over the bottom function squared, so g squared. So the quotient rule is take the derivative of the top times the bottom, leave the bottom alone, then minus take the derivative of the bottom times the top, and then all over the bottom squared. So let's look at that in action. So if I wanted to take the derivative of f of x, you take the derivative of the top. The derivative of x is 1, so I'm going to take 1 and then times the denominator, which is x squared plus 1. And then you subtract in the quotient rule, and then you take the derivative of the bottom, which is 2x, and then times the top. You leave the top alone, then all over the bottom squared, so x squared plus 1 squared. Now on quotient rule, sometimes it'll cancel nicely. So if I look at this, the numerator, if I distribute that 1, I get x squared plus 1. Then minus 2x times x is 2x squared. Then all over x squared plus 1 squared. And so the numerator would cancel to 1 minus x squared, and then all over x squared plus 1 squared. So that would be the derivative simplified a little bit with the quotient rule. Okay, let's look at the next one. So we have sine x divided by x squared. So in quotient rule, if we wanted to take this derivative, you take the derivative of the numerator, the derivative of sine is cosine, times the denominator, x squared. Then minus, take the derivative of the denominator, which is 2x, times the numerator, which is sine x, all over the denominator squared, which would be x squared squared. And again, if you wanted to make this look a little bit cleaner, it would be x squared cosine x minus 2x sine x, all over x to the fourth. Something would simplify in this. Notice in the numerator, they both have an x. So you could factor out that x if you wanted to. So you would have x, and then it would be cosine x. Oops. It would be x times x cosine x minus 2 sine x all over x to the fourth. And now you can cancel out an x from the numerator and the denominator. And so this would become x cosine x minus 2 sine x all over x to the third. And so that would be the derivative all the way simplified as far as it could go. All right, let's do a couple more with quotient rule. So our numerator is x squared plus 2. Our denominator is, t squared plus 2. And then the denominator is 2t minus 7. So for quotient rule, you take the derivative of the numerator, which is 2t, then times the denominator, 2t minus 7. Then minus for quotient rule. The derivative of the bottom is 2t, and then times the top, t squared plus 2, then all over the denominator squared, 2t minus 7 squared. And then again, if we wanted to simplify the numerator, we would get 4t squared minus 14t minus 2t squared minus 4, all over 2t minus 7 squared. And so my derivative, when I simplify this, would be 2t squared minus 14t minus 4, all over 2t minus 7 squared. The numerator, I would have t times negative 4, 2 times negative 4, which is negative 8. I can't think of any factors of negative 8 that would add up to negative 14, so it won't factor, so I'm going to leave that alone. On the next one, we have 3 minus 2x minus x squared as the numerator, and we have x squared minus 1 as the denominator. So if we want to take the derivative of this using the quotient rule, the derivative of the numerator would be negative 2 minus 2x, then times the denominator, x squared minus 1, and then minus, the derivative of the denominator is 2x, and then times the numerator, 3 minus 2x minus x squared, then all over the denominator squared, x squared minus 1 squared. And then if we wanted to simplify the numerator, we would have f prime of x is equal to negative 2x squared plus 2 minus 2x to the third plus 2x, then minus 6x, then plus 4x squared, then plus 2x to the third, all over x squared minus 1 squared. So I just multiplied out the parentheses, and then I distributed negative 2x to each of those. So now combining like terms, the 2x to the thirds cancel, and we are going to be left with 2x squared minus 4x plus 2, and then all over x squared minus 1 squared. I could factor out a 2 from the numerator, and I would get x squared minus 2x plus 1, and then this is all over x squared minus 1 could factor into x plus 1, x minus 1, and then it's squared, so I would have 2 of those. And now that numerator can factor into 2x minus 1 times x minus 1, and this is all over x plus 1, x minus 1, x plus 1, x minus 1. And then notice your x minus 1s are going to cancel in this one, so this one cancels a little bit cleaner than the earlier ones. And this would be 2 over x plus 1 squared. And that would be the most simplified version of the original derivative. All right, so now we've got a little bit of more complicated ones. So if you want to differentiate and you have 3 pieces, so we're multiplying, so we're going to use the product rule, but we're going to have to use it twice. So we have a first function, a second function, and a third function. So if I wanted to take the derivative of this, it's the product rule, and you're just going to think about it with three separate functions. So the product rule says take the derivative of the first and leave the second alone. Well, in this case, since there's two other ones, we're going to take the derivative of the first, which is 1, and then we're going to leave the second two functions alone. So 2x minus 3 and 3x squared plus 4. So that's taking the derivative of the first and leaving the second two functions alone. Now we're going to take the derivative of the second, 2x minus 3, and the derivative of that is 2, and then we're going to leave the other two functions alone, x plus 5 and 3x squared plus 4. And then we're going to take the derivative of the third function, and the derivative of the third function is 6x, and then we're going to leave the other two functions alone, x plus 5, 2x minus 3. And that would be the derivative of the original function. So the derivative of the first times leave the other two functions alone, plus the derivative of the middle function times leave the first and third functions alone, plus the derivative of the third function times leave the first and second functions alone. All right, now we've got a product rule with the quotient rule. So we've got our first function times our second function, but within each of those, we have a quotient rule. So for the first one, the derivative of 2x over x minus 1, you would take the derivative of the top, leave the bottom alone, minus the derivative of the bottom, leave the top alone, all over the bottom squared. So that's the derivative of the first function, and then we would leave the second function alone, 3x plus 4 over 5x squared minus 7. Then product rule says add in the middle. Now we're going to take the derivative of the second function. So the derivative of the second function, 3x plus 4 over 5x squared minus 7, we're going to use quotient rule. So derivative of the top, leave the bottom alone. So 3 times 5x squared minus 7. Then minus derivative of the bottom, 10x, times leave the top alone, 3x plus 4, all over the bottom squared. So 5x squared minus 7 squared. So that's the derivative of the second function. And then for product rule, we have to leave the first function alone. So 2x over x minus 1. And that would be the derivative of your original function. And we're just going to leave that alone. So using the product and quotient rule, we can find the derivatives of all 6 trig functions. Well, we know the first two. So if we have sine x, remember the derivative of sine x is cosine x. So that's one of the derivatives we should just memorize. And then we also did cosine x with its graph. The derivative of cosine x, the derivative of cosine x is negative sine x. So those are two derivatives that we did earlier. So now let's do tangent x. If you have y equals tangent x, how are we going to find the derivative of tangent x? Well, let's go down here and do some work. So tangent x is the same as 1 over cotangent x, but we don't know the derivative of cotangent x, but it's also the same as sine x over cosine x. We can find the derivative of sine x over cosine x by using the quotient rule. So the derivative of tangent x is going to be, you take the derivative of the numerator, the derivative of sine x is cosine x, then times, leave the denominator alone, then minus, you take the derivative of the denominator, the derivative of cosine x is negative sine x, times the numerator, then all over the denominator squared. Now that looks pretty ugly, but it's actually going to simplify pretty nice. So my derivative is going to be cosine times cosine is cosine squared x. Negative sine would become plus, and then it would be sine squared x. And that's going to be all over cosine x squared. But if you remember, that's one of the Pythagorean identities that you probably do remember, is sine squared plus cosine squared is equal to 1. So that entire numerator is going to change into 1. So now we have 1 over cosine squared x. But do you remember what 1 over cosine x is? 1 over cosine x is secant x. So this is the same thing as secant squared x. So the derivative of tangent is secant squared x. So this is another one that you should memorize. So the derivative of tangent is secant squared x. All right, so let's do cosecant x. So if you wanted to do y is equal to cosecant x, what would be the derivative of cosecant x? Well, let's do some work. So cosecant x, I don't know what its derivative is, but we do know that cosecant x is the same thing as 1 over sine x, I can take the derivative of 1 over sine x using the quotient rule. So the derivative of 1 over sine x using the quotient rule is the derivative of the numerator is 0, the derivative of 1 is 0, then times the denominator, so times sine x, then minus the derivative of the denominator is cosine x, times, leave the numerator alone, 1, all over, take the denominator and square it, so sine squared. So now if I do some simplifying, 0 times sine is 0, so I'm going to end up with negative cosine x over sine squared x. Still doesn't look as nice as I want it to be, so I'm going to break this into two pieces. I'm going to break this into negative 1 times cosine all over sine times sine. Well, I know what negative 1 over cosine is. That is negative cosecant x. And I know what cosine over sine is. Cosine over sine is cotangent x. So the derivative of cosecant is negative cosecant cotangent. So again, we just started with cosecant being 1 over sine x, and then we use the quotient rule, derivative of the top times the denominator minus derivative of the denominator times the numerator, all over the denominator squared, and you end up with negative cosine over sine squared x. If you split that apart into negative 1 over sine and cosine over sine, then each of those are reciprocal identities, and so you get negative cosecant x over cotangent x. Not over, negative cosecant x times cotangent x. So if you have cosecant x, the derivative of cosecant x is negative cosecant x cotangent x. All right, let's do secant x. So if y is secant x, what is the derivative of secant x? So let's go down. So I don't know the derivative of secant x, but I do know that secant x is the same thing as 1 over cosine x, and I can take the derivative of 1 over cosine x by using the quotient rule. So derivative of the numerator is 0, leave the denominator alone, cosine x, minus derivative of the denominator is negative sine x times leave the numerator alone, all over the denominator squared. All right. So if I simplify this, I get sine x over cosine squared x. And again, I'm going to separate it like I did before. So I'm going to write this as 1 over cosine x times sine x over cosine x. And I know that 1 over cosine x is the same thing as secant x. And I know that sine x over cosine x is the same thing as tangent x. So the derivative of secant x is secant x times tangent x. So going back up to our all 6 derivative sheet, the derivative of secant x is secant x tangent x. And then our last derivative that we're going to do is cotangent x. So if our original function is cotangent x, what will its derivative be? So let's go down and work that through. I don't know what the derivative of cotangent x, but I know that cotangent is 1 over tangent, so I could use that, or I could use that cotangent is cosine over sine. So if I have cotangent x, I know that that is cosine x over sine x. So if I took the derivative of this, the derivative of the numerator is negative sine x times the denominator sine x, then minus derivative of the denominator is cosine x times the numerator cosine x, all over the denominator squared. So that'd be sine x squared. Now if I multiply that out, I get negative sine squared x minus cosine squared x all over sine squared x. I'm going to pull out a negative 1 from the numerator, and then I'll have sine squared plus cosine squared, then all over sine squared. And remember from before, the Pythagorean identity, sine squared plus cosine squared is equal to 1. So that entire numerator piece right there is going to change into 1. So I'm going to be left with negative 1 over sine squared x. But remember, 1 over sine is the same thing as cosecant. So this is going to be negative cosecant squared x. So the derivative of cotangent x is negative cosecant squared x. So if we go back up, the derivative of cotangent x is going to be negative cosecant squared x. So what do you notice? What are some patterns that you see in these derivatives? The derivative of sine is cosine. The The derivative of cosine is negative sine. The derivative of tangent is secant squared. The derivative of cosecant is negative cosecant cotangent. The derivative of secant is secant tangent, and the derivative of cotangent is negative cosecant squared x. Well, one of the things that you might notice is that if the original function begins with a c, cosine, cosecant, cotangent, what do you notice about all of their derivatives? Negative sine, negative cosecant, cotangent, negative cosecant squared. If the original function begins with the c, its derivative is negative. If the original function doesn't begin with the c, so sine x, tangent x, secant x, all of their derivatives are positive. So that's one of the things that might help you remember the differences between all of the derivatives. But you should memorize these derivatives. They're not going to go away, so you might as well just take some time to memorize these each night during this unit. All right, so we are going to have a quiz next class over the power, product, and quotient rules and all the derivatives of the trig functions. So make sure that you are prepared to do those. Your homework is in your modules on Canvas. It will be one of the